I can pull it up. Yeah, hold on. Okay, so let's say we have a circuit, and it looks like this. Um, I'll put one more resistor in here, 2 ohms. And I'm going to put some nodes in here, so I'm going to label the bottom node, I'll call that V0, and I'm going to call that ground. And so you can see it's ground because I put the ground symbol there. And I will call this V1, and I will call this V2, and I will call this V3, and that is everything. Now, one thing that you can see is that I've gotten all the nodes because anything that is connected with a conductor. Oh, well, look, actually, I don't need V3. V3 is extra. V3 is the same as V0, because anything that's connected by a conductor without something in between will all be at the same voltage. So V3 has to be the same as V0. So the other voltage that I needed was not this one, but right here. And let me just make that one V3, because that one was a separate node because it is in between 2 elements. So it has a different voltage, but everything right here is at the same voltage. And then let me figure out what the current actually would be. Hold on. Let me figure out what the voltages actually would be since I made this up. Actually, I'm going to not figure out what the real answer is going to be. I'll just say this is R1 and this is R2. So that way I don't have to get the real numbers. Okay, and I'm going to say that V1 is, I'll say it is 14, and V3 is 2, and V2 is 5. Okay, so let's say that's what they are, and that's what we would get if we knew what R1 and R2 were, and we knew how to find these things. And so those are our voltages. Now, if we look at your homework question, it said, what is the voltage difference across R6? That was the first thing you needed to find. So that was an Ohm's law question. So an Ohm's law question is if you know the voltages on either side of a resistor, if you know, actually I don't think we need to know that. I think it was just the voltage difference across R6, yeah. So that would be the same as saying, what is the voltage difference across R1? So if I wanted to find out the voltage difference across R1, what I need 2 things. I need to either know the current that goes through the resistor, or I need to know the voltages on either side of the resistor. In this case, I know the voltages on either side of the resistor. This side is 14 and this side is 5. And so the voltage difference across that resistor is just 14 minus 5. It's just 9 volts. You just subtract them. Now, on the other hand, if I knew the current than the voltage difference across the resistor you find using Ohm's law. Okay, now the second part of this problem is the part that most years students have trouble with. And so it says, what if we have the same circuit, but instead of making V0 ground, we make one of the other nodes ground? And you can always make any node ground that you want. So these voltages that are listed here, these are only relative to ground. What these voltages mean is that at this point, my voltage is 5 more than ground. Right here, it's 14 more than ground, and right here, it's 2 more than ground. It's just relative to ground. So if instead I say I am going to make, so this will stay V0, but I am going to make V2 ground. So I'm going to make V2 ground. My relative voltages all have to stay the same. So I'm going to make a little chart over here that had my voltages in it. So V0 originally was 0, V1 was 14, V2 was 5, and V3 was 2. So now I have made V2 0. Now if I look at my relative voltages, V1 has to be 9 more than V2. So if V2 is 0, then V1 has to be 9. Now I'm going to look at V0. V0 is 5 less than V2. So if V2 is 0, then V0 has to be negative 5. V3 is 3 less than V2. And so if V2 is 0, then V3 has to be negative 3. And now I can see that the voltage difference for each pair of voltages is still the same. If I take V3 minus V0, I should get the same number whether I use my first column or my second column, because it's only differences in voltages that matter. So if I use my original scheme, I would have that's 2 minus 0, which is 2. If I use my new scheme, V3 minus V0, that would be minus 3 minus negative 5, or minus 3 plus 5, which is 2. So did you see how that one worked?
Yeah, that was all.
Okay, good. All right.
For number A, when you did 14 minus 5, which one? Is it always the bigger minus the smaller one?
Okay, so when you are, no, it's not. I chose it that way. So if your element is labeled, so if I had something here and it was labeled with a plus and a minus, then you take whatever the voltage is on the plus side minus the voltage on the minus side. So for instance, even if this was 10 and this was 12, then I would say my voltage here would be negative 2. Okay, this was a resistor. I don't have anything labeled, and without anything labeled, I'm going to go with the positive one. I'm just going to say the bigger side minus the smaller side is 9. And then from that, I'm kind of choosing, then what I'm saying is I'm now labeling this resistor that way. Okay, let me, okay, so it was number 9, I think, that you had asked about. Okay. So this is from the previous worksheet. I remember doing it, but I don't remember if I did it by myself or maybe I didn't record it. I don't know. Maybe I didn't post it, but I'm going to do it again anyway. It can't hurt. So, oh, wait a minute. Oh, there's my email for everybody in the world to see. Yay. No, that's not the one that I posted separately because I remember that now. I did. One, three, 4, 5, 6, 9. Should be in the second one.
Okay.
Yeah.
I don't know. I think it cuts off.
Okay. All right. Okay. Well, I'll do it. I'll do it.
It's fine. Like I can get from someone else.
If I have time when I get done doing the new ones, then I'll go back and do that one. Okay. All right. All right. So this is from today's worksheet. So we're going to go ahead and start with number 1. I picked these problems because I thought they would be helpful just looking at your homework and things that I would think you would need to know, based on what he's done in class in your homework. So this one is you're given a current and you're supposed to find the total charge entering the element at its left terminal. So I don't have a picture for you, but you can just imagine that I've got some circuit, and I've got a current entering it. Here's I, and I want to know the total charge entering the element at its left terminal. So we know that I is dq dt, which is also saying that Q, our cumulative Q, will equal the integral from time 1 to time 2 of I of t dt. And so here, our time, it says total charge, it doesn't give us time. Well, we see that time starts at 0. Time doesn't have to start at 0, but in circuits it usually does. But it says total, so that means it goes to infinity, of 20 e to the minus 5,000 t dt. So we see that we've got an exponential with a negative exponent, and you'll run across those a lot. And it's important that it have a negative exponent because as t goes to infinity, we need this to be going to 0. And we know that e to the infinity is 0, or the limit as t approaches infinity of e to the negative t is 0. Because we can't have this charge growing without bounds, so we need something that's approaching 0. So the integral of e to the ax dx is 1 over a e to the ax. That's true as long as you just have an x. That would not be the case if it was x squared. So this integral is going to be 20 times 1 over negative 5,000 e to the negative 5,000 t from 0 to infinity. Now I will take so I'll take the 20 over negative 5,000 out, and I've got e to the negative 5,000 t. Okay, that's a useless step. All right, but now I've got 20 over negative 5,000. I plug in infinity. E to the negative infinity is 0, minus e to the 0 is 1. So this is now negative 20 over negative 5,000, which is 0.004. .004 coulombs. So that one's pretty straightforward. Questions on that one? Okay. Let me